Okay, good morning, students. I hope I'm audible to you. Anish, no need to give the attendance here. We will take the IMCRP exam, and there we will be able to capture the attendance from there. Okay, first and foremost, let me share my screen. Okay, I hope my screen is visible. So in the previous class, yes, okay. So in the previous class, what we did was we studied the basics of circuit switching as well as packet switching. And as we discussed earlier, so in packet switching there are two types of switching. One is a normal packet switching, and the second one is something known as virtual circuit networks. Okay. And also in the previous class at the end we discussed that virtual circuit networks are nothing but they're a combination of both circuit switching as well as packet switching. Okay, so again we will understand how it works, and after we complete this we will start with the error control. That is, we will complete the physical layer and we will move to the data link layer. Okay, now obviously as it is written above, you can see that a virtual circuit network is nothing but it is a cross between a circuit switch network and a datagram network. So datagram network obviously means a packet switched network. Okay, and it has a characteristics of both. Now what are the characteristics? So with the diagram again you can see that it's more or less it looks like a circuit switch network, but again the working of this network it looks like a circuit switch network, but again the working of this network is a bit different and it resembles that of a packet switched or a datagram network. Okay, so as in a circuit switch network there is a setup and tear down phase in addition to the data transfer phase. So again, if you remember that in the previous class we said, or whenever we were studying circuit switching network, we saw that there whenever we wanted to transfer data, so before transferring the data we actually had a setup phase, and after the transfer ended we actually had a tear down phase. Okay, now if I give you an example, so if you have used landline phones, so whenever we are actually dialing some number, so there will be various beep sounds before the number gets actually connected. So that beep sound is nothing but the setup phase, and after the communication occurs, then there will be a tear down phase. But again in the case of the packet switch network, we saw that there was no setup phase and there was no tear down phase. There was only a data transfer phase, and how the data transfer was happening? It was happening with the help of the switches. So the switches, whenever a packet goes into a switch will get the contents of the packet as well as the destination address, and the switch in that case will help the packets to move from one source to another destination. So there was no setup phase and no tear down phase. Now again, if you remember what is a setup phase, setup phase means what? That actually there is a physical resource that is being allocated. Okay, so actually what happens is there is a physical connection that is being created between the source and the destination, so that the data transfer may occur. Okay, now again in the case of virtual circuit networks, there is a setup phase and there is a tear down phase in addition to what? The data transfer phase. So you can see that it is a combination of both circuit switching as well as packet switching. Also, resources can be allocated during setup phase as in circuit switch networks. So again, as we discussed earlier, resource allocation means nothing but a physical connection between the source and the destination will be created, and then the transfer phase will happen. Okay, so again resources can be allocated during the setup phase as in circuit switch networks, or on demand as in the case of datagram networks. Okay, now what is this? We will see in the later slides. So again, as in a datagram network, data are packetized. Okay, so if you remember that in the case of circuit switch network, we said that data is not packetized, it is actually in the form of electrical or digital signals, right? But in the case of packet switch network, we said that data is actually packetized. Okay, so there will be various packets of data and that will be sent from source to the destination. So again in the case of virtual circuit networks, we can see that data is actually packetized. Okay, so again you can see the combinations, right? So it has what? As in the case of circuit switch network, it has a setup phase and a tear down phase, as well as in the case with packet switch network, the data will be packetized. Okay, and each packet will carry a address in the header. So obviously if data is packetized, and every packet what it will do, it will carry a either a header and or a trailer. Okay, and obviously in the case of a header, it will contain what? A address. Okay, now what type of address is there, we will see in the later half of the slide. In the case of packet switch network, we saw that the address that a packet contained in the header was actually that of the destination address. Okay, but in the case of a virtual circuit network, we will see that it is different. Okay, how is it different, we will see in the later half of the slides. Okay, now however, you can see that the address in the header has a local jurisdiction. Okay, so there are two types of jurisdictions, or two types of addressing in this case. One is a global address and one is a local address. Okay, now let us understand this very carefully. Now what's a global address and what's a local address? If I am talking about a global address, it means that if a packet is being sent from a sender to the destination, from a source to the destination, the packet in its header will contain the address of the destination. If that is the scenario, it is known as what? A global address. Okay, but again, if I say that a packet has a header and the header contains the address of the next switch, okay, so a packet contains the address of a next switch compared to what? A packet containing the address of the destination. So if I say it contains the address of the destination, it is a global addressing. But again, if I say that a packet contains the address of the next switch, we call it that it's a local address. Okay, so or local jurisdiction. So which means it defines what should be the next switch and the channel on which the packet is being carried, not end-to-end jurisdiction. So again, end-to-end jurisdiction means what? The global addressing scheme. And local jurisdiction means what? The local addressing scheme. Okay, now how this works, we will see in the later half of the slide. Again, as in the circuit switch network, all packets follow the same path established during the connection. So if you remember that whenever we were talking about the packet switch network, we said that suppose there are 4 packets that are being sent from the source to the destination, these 4 packets will not necessarily follow the same path. It may travel through haphazard paths. It may travel to various paths, right? And it depends on the destination, that how it will receive the packet and how it will organize the packets in order. Okay, but in the case of circuit switch network, we saw that since there was a physical connection that was being made from the source to the destination, so obviously using that same physical path, all the data will be traveling through. Okay, so again in this case, we can see that it is again following a characteristic of a circuit switch network, that since a physical connection is being made from the source to the destination, so again using this same path, all the packets will travel from the source to the destination, unlike in the case with the packet switched networks. Okay, and the last point is nothing but if you remember that we said that the circuit switch network was actually implemented in the physical layer. Again, we said that the message switching network was packet switching network was actually implemented in the network layer. So again, in this case, we can see that a virtual circuit network is normally implemented in the data link layer. Okay, so again, to remember, just note this down, that whenever we are talking about circuit switching, it is implemented in the physical layer. Whenever we are talking about a packet switching network, it is implemented in the network layer. And whenever we are talking about virtual circuit networks, it is implemented in the data link layer. Okay, okay. Now, as we discussed earlier, that there is a concept of local addressing as well as global addressing. So if you remember that in the case of packet switch networks, so if this is the packet, so you can see that there is a data and there is an address, right? Again, there is a data and there is an address. So if there is a packet, so again in the case of a packet switch network, this address will be that of the destination. Okay, again if it is if the data is coming from the destination to the source, this address will be of the source. Okay, so that is what global jurisdiction or end-to-end jurisdiction or global addressing. Okay, but in the case of a virtual circuit network, we see that the address is not the destination address or the source address. It is nothing but it is simply called as the virtual circuit identifier, right? And what is this address all about? It just says that okay, this is the address of the next switch that the packet will go to. Okay, so this address is called a virtual circuit identifier. Now again we will see that how using the virtual circuit identifier a setup or a connection is being set up. Now if you come to a certain switch, and obviously we discussed earlier that a switch will have a routing table like this. Okay, so in the case of packet switch network, we saw that the routing table of a switch was actually of two fields. One is the destination address or the source address, and one is the port. Okay, so a port from which it was incoming and the port from which it was outgoing. Okay, but in this case we can see that the routing table of this switch, for example, will have four fields. So the first field is what? The incoming port number, right? The second field is what? The VCI, that is the virtual circuit identifier of this packet, that is coming from the port number 1. Okay, again in the outgoing side we will have the port number, which means the port through which the packet will be outgoing, and again the VCI number. What is the VCI number in this case? The VCI number is nothing but the address of the next switch. Okay, so again if you see this diagram carefully, so from port number 1 we can see that there are two packets that are incoming, right? So the first packet has the data and it has the VCI number as 14. So again you can see that the first entry in this table is nothing but the port number is 1 and the VCI number is 14. Okay, again if I go to the next packet, we can see that it has the data and the VCI address as 77. So again we can see that incoming port is 1 and the VCI address is nothing but 77. Okay, again we can see that from this switch there are two packets that are outgoing. So one from port number 2 and one is from port number 3. So again in the outgoing side of the table you can see that the port number 3 is being, and there is an entry for port number 3, and then there is an entry for port number 2. Okay, and again the data packet that is exiting from port number 2 has the VCI address is 41. So again you can see that the VCI address is 41, and again we can see that the data or the packet that is being exited from the port number 3 has the VCI number as 22. So again you can see the entry that whatever packet is outgoing from port number 3 will have the VCI as 22. Okay, now let us see, so this is for the single switch. Now let us see how actually it works whenever we are doing the setup phase. So whenever we are doing a setup phase, let's say that there are three switches like this. So switch 1, switch 2 and switch 3, right? And suppose the source A wants to send data to the destination B. Okay, now again if you see that if source A has a data to send, and suppose we name the data packet as A, so we can see that this is the data packet A that is going to the switch through port number 1. So again if I look at the routing table of this switch number 1, we can see in the incoming side that the port number is 1 and the VCI is 14. Okay, now how do we calculate this VCI? We will come to this later. Okay, so again we can see that from port number 3 of this switch 1 a packet is outgoing. Okay, so again we can see that in the outgoing side there is what? Port number 3. Okay, but the VCI is missing now. Okay, now how do we calculate the VCI? We will see later. Again, so from port number 3, if B goes to the switch number 2, so B is the packet, and suppose it goes to switch number 2. So again in the incoming port we can see that from port number 1 it is incoming, and what's the VCI? It is 66. Now how do we calculate this? We will see later. Again from port number 2 we can see that C is outgoing, so in the routing table of switch number 2 you can see that at the outgoing side it is port number 2 and the VCI is missing. Now again we will calculate the VCI later, right? So similarly C will be incoming from port number 2 of switch 3. So again you can see in the table that it is that entry is being given, and again from switch 3 the packet D will be outgoing. So again you can see that port number 3 the packet is outgoing, the VCI is missing, and again this D will be given to B, right? And the VCI number of B is, for example, 77. Okay, now let us see how this setup is actually happening. So this is the request phase. So which means A is requesting, the computer A is requesting to computer B that I want to send some data, right? And how does it request it? It will not call out computer B and say that I want to send data. It will send a special data packet. Okay, now this is the special data packet that is being sent, where we now have to calculate the VCI. Whenever the setup request is being sent, the VCIs are not there. But again, we have to see that how do we calculate the VCI so that the virtual circuit is actually formed. Okay. Now, so we have requested the setup. So a special packet from A to B is traveling through these 3 switches, right? And the routing tables of these switches are have these entry, and these needs to be updated. Okay. Now let us see how it is getting updated. So in the setup acknowledgement phase, which means after A sends the request to B, so suppose B is free and it is ready to receive the data. So what will B do? B will send an acknowledgement that yes, you can send me the data. Now let us see how it sends the acknowledgement, and let us see how after sending the acknowledgement the routing tables are actually filled up now. Okay. Now if you remember in the previous example that VCI of B was 77. So again, if VCI of B was 77, so again B will send a special acknowledgement packet, and right, and this acknowledgement packet will have the data as 77. Okay. So if you see that this packet 77 is incoming at switch 3 from port number 3. Okay. So again, if you remember in the previous example, the VCI in this case was blank, but now the VCI in this case will be updated with the number 77. Why? Because it is this packet containing the VCI 77 is incoming from port number 3. So from port number 3 you can see that the VCI has been updated now. Okay. Again, if you go to the first part of the switching routing table, so you can see that from port number 2 it will be outgoing, and the VCI is about 22. So again, whatever packet will come out of the switch 3 from port number 2 will contain the data 22. Okay. Now whenever switch 2 receives the data 22 at port number 2, if you remember in the previous example, the VCI was missing in this case, but again now you can see that it will update the VCI with the data of packet B. So again you can see that it has updated the VCI here. Okay. Again at switch 2, in the routing table what it was saying that it will send data from port number 1, and the VCI is 66. Now again, whatever packet is sent from this port number 1 will contain the address or VCI 66 as the data. Now whenever switch 1 will receive this data, what will happen is, so it is receiving from port number 3. So again, if you go to the previous example, so port number 3 VCI was missing, but now after it receives the packet like this, it will just take the data and it will update its VCI like this. Okay. Now again, from port number 1, the data that will be calculated, that will be sent, will be actually 14. So 14 is the VCI here. So again you can see that the packet D is being sent to A, right, and A will receive the VCI number as 14, right. So this is the setup phase, that's A will send a packet, special packet to B, and it will not have the VCI numbers. But in the acknowledgement phase, if B is free and wants to receive the data from A, what will B do? B will send an acknowledgement, and that will be a special packet, and using this special packet what will happen is the routing tables of all the switches now will be updated. Okay. Now whenever all the routing tables of all the switches will be updated, now we can say that this virtual circuit is complete, which means the resource allocation is done, which means the setup phase is now over. Okay. Now after the setup phase happens, what we will do? We will just send data like this. Okay. So again you can see that in the previous scenario what we sent was, we was just sending the VCI. So whenever it was going from A to B, there was no VCI. Whenever it was coming from B to A, there was VCI as data. But whenever the actual data transfer phase is happening, again we can see that this is the packet, and it will contain what? The data as well as the VCI number. Okay. So again like this. Tell me.
Sir, here for B, the VCI 77 is randomly generated, or it's giving by user?
It's randomly generated.
Okay.
So it's randomly generated, and during the session, so unless the tear down phase happens, this number will be fixed. But again, whenever for the next communication we are again setting up the setup phase, so again it will be randomly generated. Okay.
Okay.
Okay. So this is how the data transfer will now happen depending on the routing table that has been set up during the setup phase. Okay. And after this data transfer happens, what will happen? There will be a tear down phase, which means the virtual circuit that we made for transferring data from A to B is now no longer needed, and now it will be broken down. Okay. Okay. Now again, there are some important points, and so we have discussed this earlier as well. So first and foremost, let us go to the second point first. So again, we have said that it is implemented in the data link layer. So again, why I am saying this multiple times, because you should remember this, because these are important points. So a circuit switch network is implemented in the physical layer. Packet switch network is implemented in the network layer, and lastly, the virtual circuit networks are actually implemented in what? The data link layer. Okay, again, switching at the data link layer is a switched WAN. So whenever we are having a WAN, which is a wide area network, generally switching is done using this method. Okay. Now again, if you want to see what is the delay in a virtual circuit network, so again, if you just match or mix the delays of both the circuit switch and the packet switch network, so it will be easier for you to understand. So again, you can see that initially there is a setup phase. So we have seen how the setup phase, I mean how the setup request and setup acknowledgement actually works. So that will constitute of the setup phase. So there will be a delay for the setup phase, right? So after the setup phase happens, there will be no delay in the data sending. So again, you can see, if you remember in the packet switch network, there was a delay in between the packet sending from one switch to another switch. So if I just go back to the slides where we, okay, here. So again, you can see that whenever it goes from one switch to another switch, there is a small delay. Why? Because the switch in this case, in the case of a packet switch network, will have to determine everything. We'll have to determine how to set up the routing table, how to insert elements into the routing table, and again, depending on the routing table, how will it send data to the next switch. Okay, but in this scenario, the switch does not have to bother that how the connection is being made, or how the routing table is being updated, right? So the connection as well as the routing table gets updated in the setup phase only. Okay, so now the switch doesn't have to bother, or we can say that it does not take any extra time to send data from one switch to another switch. So again, you can see that there is continuous sending of data, and after the data transfer happens, it is over, then there will be a special packet from computer B to computer A telling that, okay, the data transfer is complete, whatever you have sent, I have received it, and now we can tear down the virtual circuit that was being set up. Okay. Okay. So again, in the previous class, the first point that we discussed was that there are three types of switching. First one was circuit switching, second one was packet switching, and in the case of packet switching, there are two types of switching. One is a datagram network and one is a virtual circuit network, and lastly there is a something called as a message switching. Now also we discussed that that in actual day-to-day lives we use the circuit switching and the packet switching, and message switching has become obsolete. Okay, now still we need to understand that what's the concept of message switching. So we just have one slide, and through this slide we will be able to understand that what's the actual difference between all this kind of switching. Okay, so a message switching is nothing but a packet switching network. Okay, so again, you can see in the first point that connection is the same as that of a packet switching. Okay, which means it will not have a setup phase, it will not have a tear down phase, and only the switches will on the switches it will depend that how the network is being set up and how the transfer of the data is being happening. Okay, so the connection is that connection of a message switching network is exactly same as that of a packet switching network. But okay, so in this technique, the entire message is transmitted without any break from one node to another. Okay, so again, if you remember in the case of packet switching, what was happening, that since the name is packet, which means a data is actually divided into packets, and each of these packets will travel a different route, or it can travel a different route to go to the destination. But in the case of a message switching, what we can see is that the entire message, irrespective of whether it's a packet, whether it's a signal or whatever, the entire message is transmitted without any break from one node to another. Okay, which means the switches will actually transmit the whole data. In the case of packet switching, what does the switch do? It will transmit individual packets, but in the case of message switching, it has to transmit what? The whole data. Okay, so it firstly stores and then forwards information that requires more time. So again, as we discussed earlier, that since a switch has to transfer the whole data, so obviously in the switch there has to be a memory, right? So whether so that it can store what the full message that is being incoming, it has to store it, it has to process it, and then again using that same memory it has to send it to the next switch, right? Which means in this case the switches need to have some memory. In the case of packet switching, there was no need of a memory in the case of a switch. Okay. Now again, due to this time, the access time is increased. So obvious, that is very obvious, and no direct link is present between the sender and the receiver. So that is also obvious because there is no setup phase. So that is similar to the packet switching network actually. Now if I compare this to packet switching network, again we can see the first point that in a packet switch network, information is transferred in the form of data packets between the sender and the receiver. So in the message switching, what happens? It is actually transferred in the form of the whole message. But in the case of packet switching, the data is transferred in the form of what? Of data packets. Okay. Now these packets are forwarded one by one from the sender to the receiver, right? So again, in the message switching, the whole data is being transferred, but in this case, the packets are transferred one by one from the source to the destination. Again, each packet is associated with the header. So again, we discussed earlier that in the case of packet switching, generally what happens, there can be a local address, there can be a global address. If it's a global address, it will contain what? The destination address. If it's a local address, it will contain what? The address of the next switch, as in the case with VCI, that is virtual circuit identifier. Okay, so each packet is associated with the header. Then these packets are then reassembled into the original message. But again, in the case of message switching, there is no concept of packet. It is actually the whole message. Okay, and since we are actually dividing the packets into dividing the data into packets, and these packets can travel simultaneously over different paths at the same time. So this improves the performance as well as time required to access the data packet is reduced. Okay, but this is not the same in the case of a message switching network. Okay, so I hope it is clear to you that what's the actual difference between a packet switch network and a message switching network. So again, we do not have to go to the details of how a message switching network works because it's not in the syllabus first, and most importantly, it is now obsolete. So again, but still we need to see the understand the difference between how a message switching network and a packet switching network actually works. Okay. Okay. So with this we come to the end of the physical layer. Okay. So again, what we will do is we will just go to the next slide. That is the slide of the physical detailing layer that we have prepared, and we will start with that. Okay. Okay. So first and foremost, if you remember that whenever we were talking about the detailing layer, we said that a detailing layer is concerned with mainly two things, three things. The first one is dividing data into frames. Okay. The second one was it was concerned with error control, and error control means nothing but error detection as well as error correction. Okay. And lastly, we said that it is concerned with flow control, right? So which means how the data or how do we actually send the data from the sender to the receiver. Now what is the flow control? We will come to that in the later half of the session, but today what we will see is we will just see the second responsibility of the detailing layer, and that was nothing but the error control, and that is actually nothing but the error detection as well as error correction. Now first and foremost, we will see what is an error, how can we use some extra special bits to identify an error, to correct an error, and lastly we will see some algorithms generally that are being used nowadays to actually detect and correct the errors whenever it is being sent to the sender from the sender to the destination. Okay, so again, what's the error? So data can be corrupted during transmission. So which means if I am sending data as 101 from the sender, it may happen that during transmission the data that the receiver receives is not 101 but actually it is 010. So if the data bits at some position it changes during transmission from the sender to the receiver, we call that data as an erroneous data. Okay. Now again, some applications require that errors be detected and corrected before being received. Okay, so whenever we are at the receiver side, the receiver computer will have some mechanism, or the applications that are running inside the receiver side will have some mechanism that will require what, that the errors should be detected and it should be corrected. Okay, now there are two types of errors, right? Or we can say that generally speaking there are three types of errors, for example. So first let us understand what is there in the slide, and then we will discuss the the third one. Okay, so we can see that in the first diagram we can see that error can be classified into what, single bit error. So which means whenever I'm sending data from the sender to the receiver, if only one bit, if only a single bit changes during transmission, we say that it's a single bit error, right? So in a single bit error, only one bit in the data unit has changed. Okay, so you can see in the diagram that the 0, 1, 2, 3, 4, the fourth bit is being changed from 0 to 1 during the transmission phase. Okay, so again we can see that this is a single bit error. Okay, again suppose we have another one that is known as burst error. Okay, now this burst error actually, if I further divide it into two parts, this burst error we can divide it into suppose multi-bit errors as well as burst errors. Okay, now what's a multi-bit error? The diagram given here is actually that of a multi-bit error. Okay, so what does a multi-bit error mean? It means that if two or more bits in the data unit have changed, so we call it as a multi-bit error. Okay, so again you can see that the data that is being sent is at the top and the data that is being received is at the bottom, but again you can see that more than 2 bits of data has been changed during the transmission. So there are, in this example, there are 4 corrupted bits that is being received by the receiver. So we can say that it is nothing but a multi-bit error. Okay, now what actually is a burst error? So we can say that okay, if the corrupted bits are continuous in nature, which means if I say that okay, the first 3 bits, that is 0, 1, 0 has been corrupted, which means if the erroneous bits are consecutive in nature, we actually call it a burst error, right? But if the error bits are not continuous in nature, but actually what they are, actually 2 or more bits of errors are there, but the errors are not continuous in nature, we call it as a multi-bit error. And in the case of burst error, what happens if there are more than 2 bits of data has been compromised, but the bits are actually consecutive in nature, we call that as a burst error. Okay, so again in the larger if I see the larger picture, we can say that there are 2 types of errors, single bit error and burst errors. But if I go into the details, we can say that there are 3 errors. One is a single bit error, one is a multi-bit error, and lastly there is a burst error. Okay, now there is a concept of redundancy bits. So if you remember when starting off with this slide, we said that okay, how do we calculate the data, how do we detect the error and how do we correct the errors? So we will use some extra special bits to do that. Okay, and what are these extra special bits actually called? They are called as redundancy bits. Okay, now what's the function of a redundancy bit? We will see in the later half of the slide whenever we will whenever we will study the algorithms that are being used. Okay, but for now let us understand that what is a redundancy bit. So to detect or correct errors, we need to send extra bits, and that are extra special bits, and that are known as what? Redundant bits with the data. Okay, so which means if you go to the diagram here, you can see that at the sender side, if this is the encoder, right, so there is a message that will the sender will be trying to send, and this message will be transformed into something else using a generator. And what will the message be transferred into? The message will be transferred into message plus the redundancy bits. So if I have the message as 101 and if I have a redundancy bit as 11, so the data that will actually go to the receiver side is what? The data that is 101 plus the redundancy bits that are 11. So 101, 11, this is the data that will actually go to the receiver side. Okay, and how we will see that how using these redundancy bits we will calculate we will detect the error and correct the error. Okay, now again, if the message and the redundancy bit is going to the receiver side using an unreliable transmission, and suppose we say that the error has occurred, okay, which means some bits have been changed during transmission. So again, at the receiver side, as in the sender side there will be a generator, but at the receiver side, at the decoder side, there will be nothing but a checker. Okay, so using this checker we will check that whether, using the redundancy bits obviously, so using the redundancy bits, the checker will check that whether the data that has come from the sender side is actually erroneous or not. So if it's erroneous, it will be discarded, and if it's correct, the message will be received by the receiver. Okay, so again we will see that how using these redundancy bits we are actually able to detect and correct the errors. Okay, so but for now, just remember that with the data, generally whenever we are sending data, so with the data some extra bits are being sent that will help in detecting errors and correcting errors, and these extra bits are actually known as nothing but redundancy bits. Okay, now again, so what do we do? So whenever we want to detect or correct errors, the algorithms that we have, these algorithms are nothing, these algorithms whenever we group them together, these are actually known as what? Block coding. Okay, now what happens is block coding, let us understand that in block coding we divide our message into blocks. Obviously the name suggests that whenever we are using block coding, we will divide our message into blocks. Okay, now if you remember that we said that what's the first responsibility of the data link layer? The first responsibility of the data link layer was nothing but it will divide data into frames, or in this case we can say that it will divide data into blocks. Okay, so again, if you just look at the definition, you will be able to understand that in block coding we divide our message into blocks, and suppose we say that each block is of k bits of data, right? So suppose in this picture, if you see the first picture, we can see that the whole message is now divided into what? Blocks of data, and all these blocks are containing what? K bits of data. Okay, and this k bits of data, so all the blocks are known as nothing but data words. So these words are very important. Why? Because we will use these words in the later half of the slide. Okay, so the so in a block coding we divide our message into blocks, and each block will be of k bits of data, and these blocks will be in turn will be called as what? Data words. Okay, and after we add the redundant bits, so if we add r redundant bits to the data words, so we can say that, so after we add the r redundant bits to the data words, the data words will now become what? Nothing but code words. Okay, so this this word is also very important. Okay, so if we divide a message into blocks of k bits each, so these blocks will be known as what? Data words, and to this data words, if we add some redundant bits, that will enable us to detect and correct the errors. So this, after adding the redundant bits, these data words will now be called as what? Code words, right? And what will be the length of the code word? It will be n, and where n is equal to what? K plus r. So k was nothing but the length of the data bits, and r is nothing but the redundant bits that we are adding. Okay, so again, after adding the redundant bits, the data words will now be converted into code words, and again the length of the code word will now be equal to n, where n is equal to what? K plus r, where k is the number of bits in the data word, and r is the number of bits in the redundant bits. Okay, I hope I'm clear till this. Okay, so using this coding scheme, if I give an example that the value of k is 4, which means there are 4 bits in a data word, and the value of n is 5, which means there are 5 bits in the code word. So as we saw, so using the previous example, so 2 to the power k, so very sorry for my formatting, but this will be 2 to the power of k. Okay, so if 2 to the power of k, so if 2 to the power of 4 is 16 data words, so if we have total of 16 data words, and 2 to the power n will be 32, so we will have 32 code words. Okay, so if you see this previous example, just a second, if you see this previous example, we have using the next set of example, we will have what? 16 data words, right? And how many code words we will have? We will have 32 code words. Okay, so I hope the example is clear to you. So using this example, if k is 4 and n is equal to 5, so we will have 2 to the power of k, that is 16 data words, and we will have 2 to the power of n, that is 32 code words, right? So we saw that 16 out of these 32 code words are actually used as a message. So as we discussed earlier, that 16 data words are actually the messages, and the rest of them are actually what? Redundant bits, and these bits are nothing but they are used to calculate the errors, and the rest of the bits that are the redundant bits are either used for other purposes or they are unused. Now what are these other purposes? They are used to detect the errors as well as correct the errors. Okay. Okay. Now, so again, as we discussed earlier, there will be two steps. One is error detection and one is error correction. So again, if I come to the error detection part, and if I see the diagram here, so again we can see that at the sender side there will be an encoder, and there will be a data word, and obviously we have said we have seen earlier that the data word is of what? K bits, and again there will be a generator. What will the generator do? It will just add redundant bits to the data, and after adding the bits, redundant bits, the data word will be converted into what? Code words, and the size will be of n bits, right? And suppose this code word is now sent to the receiver side using a unreliable transmission. Okay, so when the receiver will receive the code word of n bits, the code word will now be moved into the checker, right? Now what will the checker do? It will first detect the errors. Okay, if there is any error, it will discard the message. If there are no errors, what will it do? It will just extract the k bits from the n bits. Okay, so what will it actually do? From the n bits, it will just subtract the redundant bits. So after subtracting the redundant bits from n bits, then we will be only left with what? K bits, right? So what will the checker do? It will just discard the redundant bits. It will just extract the data, and the data, as in data word, will now be given to the receiver side. Okay, so I hope I am clear with this diagram. Okay, next, so whenever we suppose we have a data table like this, so if these are the data words, so if the data words is 0 0 0 1 1 0 and 1 1, so suppose these are the data words, and suppose we are adding one redundant bit each to this data words. Okay, so if I add the redundant bits, you can see that, so this 0 0 will become 0, which means the last 0 is the redundant bit here. The 0 1 will become 1, which means 1 is the redundant bit here. This 1 0 will become 1 0 1, which means 1 is the redundant bit here. And if this 1 1 will become 1 1 0, which means 0 is the redundant bit here. Okay, so again in this example, if we see, then let us assume that k is equal to 2. So again we can see that in the data words the number of bits are actually 2, so k will be equal to 2, and n will be equal to 3. So which means after adding the redundant bit, there will be 3 bits in the code words. So again this table will show nothing but the data words and the code words. So later we will see how to derive a code word from a data word. Okay, so we will see that whenever we will go to the algorithms that are actually used to detect and correct the errors. Okay. Now again, so let us assume that the sender encodes the data word 01 as 011. So we can see that we have given the table here. So if the sender encodes the data word 01 as the code word 011, right, and it sends it to the receiver, we can consider the following cases that can happen. Okay, so what's the first case? The receiver receives 011. Okay, so it's a valid code word, right? The receiver extracts the data word 01 from it. Now how do we extract this? We will see in the later half, but still in this example we can see that just removing the code word, it will removing the redundant bit, it will extract the data word from the code word. Okay, so this is the first scenario if there is no error. In the second scenario, if the code word is corrupted during transmission and suppose 111 is received, right? So again 111, if you see this table, 111 is not a valid code word here. So again, if it's not a valid code word, what will happen? This is not a valid code word and it is discarded. Okay, and what's the third scenario? The code word is corrupted during transmission, which means some of the bits has changed, which means a 000 is received. Okay, so again if a 000 is received, so we can see that 000 is actually a valid code word. Okay, so if a 000 is received, this is the valid code word. The receiver will incorrectly extract data word 00. Okay, So which means 2 corrupted bits have made the error undetectable. Okay, so again we will see that using error detection and correction, using some algorithms and using some methods, we can calculate that okay, this algorithm can detect single bit errors, this algorithm can detect 2-bit errors, this algorithm can detect 3-bit errors, and so on. Okay, so using some methods, and we will see in the examples that we can safely say that okay, if I use this algorithm will be able to detect this many amount of errors. Okay, so in this example, if you see that if there are 2 errors, this method will be unable to detect the error. Okay, so again, an error detecting code can detect only type of errors for which it is designed, which means if I design a code or design an algorithm for detecting 1-bit error, it will be able to detect 1-bit error. If I design an algorithm to detect 2-bit errors, again it will be able to detect 2-bit errors. Okay, so again, error detecting code can detect only the type of errors for which it is designed. For the other type of errors, it may remain undetected. Okay, so again we will see the specific scenarios where we design algorithms to detect 1-bit or 2-bit errors. Okay, okay, so if I go to the error correction part, right, so that was error detection part, and this is the error correction part. So again, if you look at the diagram, you will be able to understand it better, that the sender using an encoder will be trying to send what, k-bit data word, right, and using the generator, what will the generator do? It will add redundant bits to the data word. Okay, so after it adds r redundant bits to the data word, it will become k plus r. So k plus r will be nothing but n. So this will become what, the code word. Okay, now again, if this code word is being sent to the receiver side using unreliable transmission, what will happen? The receiver will receive the code word, right, and it may happen that in the code word some bits have changed, so it's a erroneous code word. Now what will it do? It will go to the checker. Okay, so the checker will not do nothing. It will just take the code word. It will correct the code word, right? How will it correct? We will see in the later half of the slides. It will correct the code word, and what it will do? It will just after correcting the whole code word, it will extract the data word and it will send it to the receiver side for accessing. Okay, I hope I'm clear till this. Okay, so again, very quickly, if I go to this example, so if we have a table like this, and so we can see that the data words here in this example are actually of 2 bits. So the value of k is 2, and the code word is actually of 5 bits, which means 3 r bits have been added, and the total value of n will be what, 5. So there will be 5 bits in the code word. So again, if I encode this data word into this code word, so let us see what happens. So let us add more redundant bits. Okay, so in this example, to see, we can add 3 redundant bits to the 2-bit data word to make a 5-bit code word. Okay, okay, so assume that the data word is 0 1. Okay, so what I'm sending, suppose, is 0 1. So suppose I'm sending the second data that is in the table. Okay, so suppose let us assume that we are sending 0 1. Now the sender will create the code word as 0 1 0 1 1. So again we can see in the code word in the second row that the code word is, if I am sending 0 1, the code word is nothing but 0 1 0 1 1. Okay, so so during the transmission, the code word will become what, 0 1 0 1 1. The code word is now corrupted during the transmission. Okay, and 0 1 0 0 1 is received, for example. Okay, so again, the first what will the receiver do? The receiver will find that the received code word is not in the table. Okay, so it is receiving what, 0 1 0 1 1. So again we can see that 0 1 0 yes, so we will find that 0 1 0 0 1 is not in the table. So the receiver will say that okay, this is a erroneous data. Okay, so this means that an error has occurred. Obviously, the receiver, assuming that only 1 bit is corrupted, uses the following strategy to get the correct data word. Okay, so very quickly, we have 1 minute left. We will see the strategy here. So comparing the received code word with the first code word in the table. So I will compare what, 0 1 0 0 1. This is the code word that we have received, and we are comparing this to the first code word, that is all are zeros. The receiver decides that the first code word is not the one that was sent because there are two different bits. So obviously there are two different bits here. By the same reasoning, the original code word cannot be the third or the fourth one. So again we can see that there are 2 or 3 different bits here. Okay, so the original code word must be the second one in the table because this is the only one that differs from the received code word by 1 bit. So assuming that only 1 bit is erroneous, and using this strategy, it may detect that okay, this is the actual code word, and using this strategy it will just take out 01 as the data word and it will send it to the receiver side. So this is not an actual example, but we can see that okay, this is how the error correction works. Okay, we will discuss on this in details in the next class. Okay, so it's already 10:20. Let me first just stop this sharing. Okay, so your exam starts from 10:20, right? And your exam will end at 10:30. So just a second. Okay, and I hope all of you have got the IMCRP exam code in your WhatsApp groups. So I request you to go and give the IMCRP exams because that is very much mandatory for your attendance. The exam time is valid till 10:30. So in between that, if you are facing any difficulties in giving the exams, I will be here till 10:30. Please come back to the meeting, inform me, and I will unlock you. Okay, so just go and give the exams. Thank you.
Thank you, sir.
Yep.